Vertical mixing near the ground. Vertical or turbulent mixing in the atmosphere can be thought of as the exchange of well-defined air parcels. So we're going to assume that parcels will mix in the vertical, conserving their value of mixing ratio, and do so dry adiabatically so their value of potential temperature does not change. In the schematic you can see a wind profile which increases with height, and two sample parcels, one near the surface in green and one at the top of the mixed layer in blue. And so parcels from the top are advected down to the bottom of the layer, and parcels from the bottom of the layer are advected up to the top of the layer. If you do that over the entire column, what you will find is that the net resulting temperature and dew point profiles should be represented by a dry adiabat and by a line of constant mixing ratio. We have a trace here for Cobar, and on the right hand side you can see the wind profile, and it's really quite strong, and so one should expect mechanical mixing happening through that. The dotted lines represent the top and the bottom of the well mixed layer. You can see the well mixed layer by the fact the dew point profile is very close to the anisoplectha of mixing ratio, and the temperature profile is essentially a dry adiabat. At the top of the layer we have an inversion, which is most probably a substance inversion, and at the bottom of the layer we have what's likely a radiation inversion. Remember, this is an evening radiosonde, and so surface cooling means that there's an inhibition of vertical mixing. So the temperatures decrease via long wave cooling, and the moisture doesn't get mixed through the depth of the atmosphere, so the surface dew point increases. But to reiterate, there's the evidence of the mixed layer. So parcels of air mixed through the column of atmosphere, conserving the value of potential temperature such that the temperature profile is a dry adiabat, and conserving the values of mixing ratio such that the new dew point profile is an isoplecth of mixing ratio. So consider two samples of air. You've got one at a pressure P1 aloft with a mass M1, mixing ratio R1, temperature T1, and specific humidity Q1, and lower down at a pressure P2, a mass M2, Q2, R2, and T2, and they're going to mix together at an intermediate pressure level. So assume the mixing takes place after the two samples are brought adiabatically to a common pressure, and so we can write then the temperature of the first air mass 1 at this pressure and use Poisson's equation as shown, and then the second air mass is brought down to the same pressure, and so it has a new temperature after that mixing in the vertical. T2P is equal to T2 P on P2 to the R and Cp, so again using Poisson's equation, and then we can use the mass weighted mean temperature to get the mean temperature, and it's shown in that equation there. So we substitute in the equations for T1 and T2 at the new pressure P into our equation for the mixed temperature Tm at P, and you multiply both sides by 1000 on P to the R and Cp, and so you end up with that mixing these two masses you get a mass weighted mean potential temperature. So it's a the mass weighted contribution between the two initial potential temperatures. And we've done this for two levels, and now you can generalize that for a column of air. And if the column of air is mixed purely adiabatically, it will have a constant potential temperature theta m, which is a weighted mean of the thetas of all the infinitesimal elements in the column, which is precisely what we saw in the previous slide. Just to go back, the two previous slides, that the temperature lapse rate is now the result of mixing parcels right through the depth, conserving the value of potential temperature. Here's what this looks like on a skew T log P aerological diagram. So the brown lines indicate the mixing layer depth. And so because parcels of air are conserving the value of potential temperature, and we're going to establish a mean potential temperature at each level, we use the equal areas method. And so in this case we choose the value of potential temperature that has equal areas to the left and to the right of the temperature profile. Likewise for the mean mixing ratio. And so once you do that, you establish the new temperature lapse rate and the dew point temperature lapse rate.